All right, welcome back everyone, and today is the day. Today we're finally going to start building our IK rig system in WebGL. All right, all web-based, all real-time. All right, so I'm really excited. I've been waiting for a year to do this, and I finally built it. So it's a great accomplishment, and I'm just happy to be able to show it off and really teach everyone else to do it. So today we're going to do the first video, which we're going to do with hips. So how do we apply hips to different bone structures? So right now, let's look at what we got. So the centerpieces are animation skeleton that we're going to be sampling. And to our right side, we have Vegeta, which is basically the same skeleton, but shorter. He's a shorter guy. He's only 1.69 meters tall. And to our left, we have a robot dinosaur. So this is going to be a robot dinosaur. And like I said, we're dealing with hips, and we're trying to build a system like the Ubisoft, which can be applied to any rigs, ideally. Ideally, you want to be able to take an animation and try to apply it to a rig that it doesn't even follow the original animated intent. So it's hard to tell the axis from this animation because of the scaling issues. That I can't fix because the source is scaled, but we can tell by what our target are. So we obviously our source and our Vegeta, they actually have both Mixamo skeletons. So overall the orientations are about the same. It's kind of hard to tell, but the legs of the source is actually backwards. I actually changed Vegeta's to be forwards because when I started doing IK with the Vegeta model, I wanted things to be easier to use. So for that sake, that's why the bones show that forward direction is forward, and left points to the right, actually, because it's upside down. Now, since today we're dealing with hips, like I said, the hips are the same. Like for these two, they're about the same type of hips. But now the problem is this guy. This guy's hip bone is completely different. It's pointing backwards, it's laying on its side, it's not following the same rules as the source file. So the idea is like, well, how do you apply this, right? Let's make sure I don't mess up the recording. So that's the thing. It's like, how do we apply the hips rotation when it's so different? You know, even if we do like animation retargeting like it did like 10 videos ago, it won't work because the structure has to be similar. But the structure is completely different. So that's going to be the whole point of this series, is because this skeleton needs to walk like that skeleton. So by the second version, I finally came up with a perfect solution. I actually just stumbled on it. It was just an accident. It was just like 10 or 15 or 20 failures in. I was just so tired or exhausted. And I had this flux capacitor moment where I just had like, you know what? What happens if I invert the Quintorian and then apply it to an animation? And then, you know, use that differently. And I just experimented, I played around with it, and it gave me the solution to the hip and the overall IK problem, to be honest. It like, the second version, once I figured that out, it actually improved version 1 by a tremendous lot. It made the code simpler, it was easier to maintain, and everything else. It just did an awesome job. It came down to the point that it replaced a lot of things. That my aim IK thing worked all right, but this new idea actually improved the aim IK a lot better. It just, I don't know, it just blew my mind. Like I said, it was my flux capacitor moment. So that's why I created a video called the Quintorian Inverse Direction, because I have no name for it. Like I said, just something I did because I was tired of failing, so I just messed around. And ideally, it's one of those things that just, when you mess around, they create the thing that you need to complete your project. So, like I said, we're going to create this fake direction that we can then apply to all the things. So the idea is, I don't care what the orientation of that bone is. I don't care the orientation of that bone is, and I don't care the orientation of that bone. To me, they are all going to be pointing forward. And so I'm going to say there's going to be like a look direction, and there's going to be a twist. I think this one I can't remember if I'm using the twist direction or twist numeric value. We'll see the code in a second because I rewrote this like a few times just to fix things up. So I don't remember because I've been so busy. So that's the idea. But for sure, everything's pointing forward. Everything's gonna be axle aligned to the forward direction. So this way, when this changes the this alternate forward direction, I can just say, well, just apply that alternate direction change to this alternate because the alternates are all the same. So it's gonna have an alternate access by using the inverse quaternion of each hip. So this way, each hip will actually have a different direction, but in the end, it always points the exact same direction. It doesn't matter, basically, which skeleton I'm working with, which makes it more universal, which is great. I have no clue if the Ubisoft invented this themselves, and I just stumbled upon it, or I just came up with something cool and neat that works. All right, so that's the idea. So that's about hips. So that's the grand piece of the hips, because it was the starting point of a lot of things. It actually helped fix the spine. Okay, so in this case, we're going to be using a direction, and then we're just going to use the angle of rotation. As I was building these videos, like I said, I created a third version, 2.1, and I realized that using the twist numeric value works all right. But if you want to recreate the animation even a little bit better, it's actually better to use a twist direction as opposed to a number. But for this example, it works just fine. But like I said, I kind of left it this way, so we do it one way and then we do it the other way, because who knows, maybe the twist number works better for other things and the twist direction works better for something else. For me, the twist direction actually works for most things, to be honest, when it comes to the IK, by the time I was done with version 2.1. So and now so that's all about rotation. Now the hip is the only bone, ideally, that you're going to deal with more than just rotation. Every bone is going to be just rotation related. The hip bone or the root bone is going to have position. So you need to be able to translate the position IK wisely-ish through it. So the only solution I came up to is to kind of scale it. You have to scale it in some fashion. So I used the concept that I kind of came up with, or whatever, for the retargeting animation video. So the idea is they're going to take the height of the hip, and we're going to use that the difference between from one structure to another to actually create a scalar value, and then we use that scalar value on the actual movement. So if the source video has like an origin value, let's say the source hip has the origin of 0, and it moves like 10 steps forward, its movement is 10 steps in the Z direction, and that's going to be our movement. So we're gonna save the bind height. So what is the height of the skeleton? So it's going to be a 3, and then we're going to say, well, the other skeleton, the height is a 4. So what you do is you take, well, we're going to step through this later, so I'm not going to waste too much time on it, but this is basically how we're going to create some a movement and then apply it to all the other skeletons in the future. And we're just going to use a scalar value that we'll have to compute for every skeleton to translate that movement. But when it comes to rotation, we're just going to have a look direction, kind of like how you do a look, quaternion look at, or like a matrix look at. We're going to do something like that. But it's going to be it's going to be a swing. It's not going to be a complete look. It's going to be a swing. And then we're going to apply a twist. So that's our data type. So this is the data hip. That's all the information we need to do IK movement with the hip. So we're going to start filling in our IK compute. So we're going to tell our pose. So after we animate the pose, we're going to say update the world position, because we need the world position and world rotation of all the bones in the pose. Because when it does the computing, when I write the animation, only thing is changes the local space, and that's what usually animations is. It's just a change in local space, not actually the world space rotation and position. So you got to just compute the world space, and then everything's good, because we need world space information to actually do all our IK, and then we convert everything back to local space. All right. So the first thing we're going to need is we need to get our bone information. So our hip is going to be the bone that we care about. And then the next thing is we're going to get the bone information related to the animated pose, and then we're going to get the information of the bind pose for the bone. So the rig system contains the working pose that we're working on, and then the bind pose. So this way we know what its T pose is, its starting position. Like I said, the skeleton does not need to have a resting pose in a T, as a T. It can have a resting pose as an A, but you need a T pose specifically to do a lot of this IK stuff. Like I said, it just makes it super easier to move things around when everyone's kind of sharing the exact same kind of general position, or like same general pose. Because it's easier just to rotate things when you know where they are, when they all kind of match up. All right, so so now we don't have this information. Now we need to create those alternate directions. Like this part right here is, like I said, it's from the previous video. So we take the world space bind rotation, we invert it, and then we do a transformation of a vector. So like I said, I'm going to say the forward, alternate forward, is going to be the world space forward, and our twist value is going to be dependent on our world space up. So we use the inverted quaternion that gives us new direction. So this is going to be our direction that translates forward and up into whatever orientation that bone is. Like I said, dino bone hips are completely different from our human hips. It's pointing in different directions. So this gives us like a Rosetta Stone, basically, like from French to English type of translation. So like I said, all our hips have a forward and up, and we're just translating that back to what that structure is. So once we know that structure's direction, then we use the pose that we're working, the animated. We take the rotation of that world space rotation and transform that direction to get us the pose forward and pose up. So now we know what the forward is. So the pose forward is where it would be if it was actually that forward that moved, not the actual forward that is related to that orientation. So I have a bunch of visual debugging stuff. I don't remember, so let's see. Oh, you know what? We got a couple of things I forgot to do for all this talking. So first thing, let's get rid of all these models that we don't need to be able to see, and let's animate. Let's run the animation. Just one frame of animation. That's all we care about. We're not going to do too much. So there we go. So there's our structure. It's animated, and so the white lines this is the forward direction, and that's the up direction. Now, when I created the alternate, let's go back down here. So so that forward and that up is the white lines, right? So right there's the white lines. We translate it and then we rotate it based on the animation. So the orange line is exactly where that forward would be based on the hip movement that was actually done. So like I said, we're making everything axis aligned, and then we're seeing where the axis line moves. Like I said, we translate everything to like a universal direction, basically. So it's like universal direction. So that forward line, when it's animated, it actually moves over there. So that's going to be our swing. So we're going to swing from this direction to this direction. That's simple enough. And that's the same thing when it comes to our twisting. So if that's our up, that means all we got to do is twist in that direction. That's just the angle between the two is our twist value. Super simple, right? It's super, super simple. And there we go. Let's see. Do I need to save position? No, I actually recreate position. Sweet. All right, so that's what the data looks like. So once we got our alternated position, now we know where everything is in world space in related to our special alternate directions. So now we take so like I said, we just have to figure out our swing, where swing is between that white line and the orange line. So once we have the swing direction, we apply it to our world position root. And that's it. So that's all we got to do. Since there's no apparent bone to our hips, I don't need to do anything else. So most often you're not, but if you have like a root bone that your hip is attached to, you might have to do something a little bit different. But in the other videos, we do that thing. So you can always just translate it into the hips if your structure really needs it. But like for this example, I wanted to keep this nice and simple as the starting point, because we're going to do it with other things in the future videos. So that's our swing, right? So we got our swing rotation, very simple, just like our swing twist video I did like previously. And now we just have to compute our upswing. So now I know where my upswing is. I just take this upswing and my pose up and just get the angle between the two. And let's see. And I have some debugging stuff we can watch. As you can see, I'm a horrible typer. That's why I don't want to code lively. And there you go. And as you can see, the orange. So the white is our swing animation, and so it's our. This is the pose animation. This is what we first used to help compute the swing. And now we have a swing forward. So we compute the swing forward just for debugging. And the idea is that, as you can see, the orange and the white line up. That means our swing rotation is perfect. It actually rotates exactly where we need it to go. That's perfect. So now that our rotation now has a singular axis, that means our up direction and our twist direction are on the exact same axis. So all you have to do is just get the angle between the two. And that's what this part is. So there you go. Now we know the twisting, because you got to think about it. We're going to do a swing and twist. So once we swing our bone, so now that the white matches the orange, so all we have to do is then just rotate on that axis. Just use that, like we do an axis angle. Like most Quaternion libraries have an axis angle. So you use that direction, the look direction that we want, as the axis of rotation, and then just the angle between to cause that twist. Ooh. And yeah, that's pretty much swing and twist right there. And then you just got to do a couple of things. Like, I don't want to go through much about this card, because there's a video about swing and twist. So this is just to continue. This is just reusing that swing and twist video to compute the to make sure it's a negative or positive. And when we're all said and done, so that's all the rotation. So that's the end. So right here, when we have hip direction copy, we're going to use the pose direction as our look direction, because that's the direction the animation is pointing when we use our alternate forward. Like I said, we're going to use all our alternate forwards, all directions that have been rotated as our directions in the IK. Because like I said, if we create this universal direction system-ish type of thing, I guess you can call it, or just say that everything is aligned, it becomes super easy to reuse everywhere else. And like I said, the whole movement part of it is like the bind height. We just usually the Y position of our pose, of our position, world space position of our hip. That becomes the bind value. We're going to see how we use that later. And then the movement is we take the starting bind position, and then we subtract it from the pose world position. So this way, the starting position of our T pose, starting, and then where the animation took it, and just find the difference. So that's our movement. That is our movement in relation to this bind height that we're going to use. So we're going to scale it forward. And that's it. And the way we visualize it, we're going to run a visualizer. So we're just going to say, here's the IK information that we're going to pass in, and this is our rig. And all I need to do is just get the world position of the hip bone that we want, that we're using, so I know it's world space position. So this way I mark a spot saying, okay, this is where our hip is. and then we just create a line to with our hip, with the hip direction is going to go, and that's it. If I were to do like twist direction as opposed to like twist the degree radians, I would do up direction as well. And when we visualize it, this is all we're gonna get. So that's our point, and that's the direction. So that's our IK information visualized, basically. I'm just not visualizing the twist, but that's where the hip points. So how long is this video? Oh my gosh, 20 minutes already. I'm sorry. I'm trying to keep these videos under like 15 to 20 minutes, and I still gotta go through how to apply it. All right. So here's the thing. So we have our IK information. All right. So the only thing left is that we have to apply it to our skeleton. So let's load back Vegeta, and let's load in his mesh, not just his skeleton. I set this up so I can very easily edit things. So if I go back, so there goes Vegeta, and he's already in position because the code's running. So back here in the source, like I didn't really show you this part, but in here, in the load source animation, I create a closure or an inline function. I don't know whatever you want to call it, and it just does all the code for me. So right here, like it runs the animation, it applies the pose. So this way I can see the animation source. Then it runs the compute, and then it runs the visualization. And if pose A has been loaded in, just say, okay, you know, IK pose, apply it to this rig. And like I said, it's going to be the exact same IK information, and it's going to, like, I'm not changing it to work better for the dinosaur. It's going to be the exact same IK information, and I'm just going to apply it to the dinosaur as well, and just apply pose. So this way we can actually see it. So it's rendered. All right then. So how do we compute how do we apply that IK information that we created, right? Let's see, where are we? So we have all this information filled in. Now how do we apply this? So apply hip. There's a bit of code in here. So we're going to do this a lot. We're just going to grab all the information that we need. We need a T pose. We need the pose for our Vegeta or dinosaur. So we're going to do apply IK and swing. So the first thing we do, we need to get the world space position of our hip. Now, since the bone is, since the skeleton or the armature, or since the hip in our skeleton does not have a root, then it's basically the local space. Local space is this. I kind of, like I said, if hip had a root, this is what we definitely have to do, because let's say if we move our root and then we need to do IK in relation to hip, we need to know where everything is exactly. So the first thing is we're going to get the parent root of our bone, and in the case of the hip, there's none, so it's going to return back a rotatorian that has no rotation at all. So it's an empty rotation. So that's what our rotation is going to be. I can even say that in case the hip isn't the root bone, but in our blah 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 example they are. Okay, so now that we know it's our parent rotation, we're going to then take our local bind location, and apply it to the parent. So the idea is that we're not gonna get, this is how we're gonna get the world space. So we're gonna like take the bind pose, like that local space bind pose, and then bring it into world space. So this way is like, where would this bone be? Where all its parent bones moved, but that bone specific did not move at all. It's like, hey, so this is where it exists now. This is where it exists if it did not move, but everything else behind it that's attached to moved. So it's kind of like me moving my my hand. My hand keeps changing, but my finger stays the same. My finger's still in its bind pose. So that's what we're doing. I want to know where my finger is. My finger exists in different parts of the world space, because my hand and my arm is moving it. So that's why we're doing this. All right, so now we need to create our swing rotation. So we know our hip is supposed to be forward. Our hip is supposed to be forward. It's supposed to align. I don't care if it's the dinosaur or Vegeta. It all is forward. So because we're using this alternate direction. So we say we move forward and then the hip IK direction. So it's that forward to the IK direction creates our swing. And then we apply it to our local space, like our world space unmoved bone, like the finger. We're going to apply it to his finger. So now we're going to do that swing, and now it's going to be like, bloop. We swung it in some direction. And so now we applied some actual rotation to our unmoved bone. If the twist is not equal to 0, like I say, we take the hip direction as our axis of rotation, and then we say what radians and angle that we want to rotate it by. And when we're all said and done, we take the world space, which isn't, like I said, it's an empty rotation, and we invert it and we pre-multiply it. So this basically saying this inverted, so it's like inverted parent times Q, because that's what Q is. So it's basically backwards. So instead of, because when you read it, some people might get confused and might think it's Q times inverted parent, but it's not. It's inverted parent times Q. That's why it's pre-multiply. It goes before it. So there you go. Because like I said, I write my own math libraries, so this might be a little confusing for some people. Now with our rotation all computed and in local space, because this is how we convert to local space by doing the invert of the parent, we save it right back into our pose that we want to animate. All right, so now we need to deal with position because the hip is going to move. The hip is, because we're in a walk cycle, we're going to move forward, we're going to move up, we're going to move somewhere. So first we need to create a height scale. So we take the bind height and then we divide it by y. So our current model that we're trying to animate, we want its height and we apply it. So how do I know this? Well, the idea is that I know my source height equals some value, and I want to multiply it by a scalar that then will make it equal my target height, right? So we have source height times scale times target. I don't know what my scale value is. So if you just use basic algebra, we just say our source height gets divided on the other side. So now we have scale equals target height divided by source height. That's our target height and that's our source height. That creates our scale value, because that scale value translates from one system to another. And like I said, it's simple algebra. Because I didn't go to college, so the only thing I know is algebra and a little bit of trig. I've gotten pretty far with just knowing that much. I failed calculus on my online calculus course that I did like a couple years ago. All right, so there you go. That's how I came up with that. That's how I figured it out. So once I have that scale, I take that movement and just scale it, right? And then just add it to the starting position of the skeleton. So like I said, this actually scales the movement perfectly. It does a good job of scaling the movement. So if it rescales the movement, so that's like if I stand up or move forward, it actually keeps the feet without doing any like extra IK to make the feet touch the floor. It actually does a really good job of keeping the feet where it needs to be. So it does a really good job. It's so simple, but it works. And then we just set that position. So pretty simple. So if I click that, if I come back to here, that's what we saw. The body is moved. So now let's animate the thing. So I'm going to switch this out to animation loop, refresh, and there you go. And it's going slow because I have the animation going at a slow pace. So how about we do it fast and then refresh. It's hard to say. It's hard to say. Let's go back to 2. But yeah, we can't see the, like I said, I don't have any visualization for the twist, but it does the twisting. It rotates and does whatever it's got to do. And like I said, the feet's not touching yet because we need to move the feet based on where these feet are. And there you go. That's how you translate the hip IK information. Let's see. Can we? Now we just bring in Dinobot, not Dinobot, and let's bring in the skeleton. Not the skeleton. The mesh. Oh boy. There you go. And that is how we translate. And all the movements is scaled to the character. So the source character is taller. So he's actually going to walk faster. And Vegeta and the dinosaur is a little shorter than him. So that's why they don't match up. Because everything is scaled to that specific model's height. So yeah. I don't know if it's going to be that concept is going to be perfect for all things, but I think if you're dealing with most characters, it works very well. Like I said, I've tried a couple of other models and even proto rigs, and it works just fine. So it's one solution. It's one solution to the problem. I'm sure there's a better solution, but good enough, right? I'm not Ubisoft. I don't have a team of mathematicians to help me. So simple works as long as it gives you the right direction. So there you go. There you go. That's our IK information. I got it done in 32 minutes. I don't think there's anything else I really need to explain. I hope I explained it well enough. I'm talking fast. I usually don't talk fast. I'm usually a very slow talker. So I'm not actually going back to my normal voice. I talk fast sometimes when I'm actually excited, when I'm happy. So if you see me talking fast, that's usually a good sign that I'm in good spirits. I don't want to waste too much time. But yeah, I'm excited. I'm happy to finally be able to do this, and I'm really happy to finally share this with everyone and really teach people how to do it. The code's all going to be on GitHub. It's all up on GitHub already before even to create all these videos. So feel free to learn. Take it if you want to use it. If you make boatloads of money off it, please share it. Because I initially, when I made first one, I actually tried to sell it. No one was biting. So if you make money, hire me and give me some money, please. Because this is like a year worth of work that I did. But like again, I'm not expecting anything. It's better off people just know how to do it, and hopefully someone will teach me better ways to do this, so this way I can have a nice, good animation system when I start making my game someday. So there you go, that's hips. In the next video, we're going to deal with limbs. We've done limbs a year ago with the original solvers, but we're going to deal with it a little bit more. So hopefully the next video will be quicker because it's I'm not actually dealing with the IK solver itself. We're just going to say we're just going to use the solver. So yeah, that's it. You know, the coronavirus is still happening. This is my corona beard. It's growing very nicely in lockdown. I'm not shaving at all. I'm going to see how long it gets. So this is my wizard beard that I'm developing for these videos. So I guess I'll see you next video about limbs, then feet, and then everything else after it. See ya.